Hey guys, welcome to Crown Smart. In this video, we want to talk about first we are going to talk about the usual topology, and then we will talk about limit points. Okay. Now, first of all, in my last video, I gave types of topology. I gave the indiscrete topology. I said something about the indiscrete topology. I say where X is remember, X is non-empty. X is an arbitrary set that is not empty. Now, for the indiscrete topology, we have that indiscrete or the trivial topology. We have the topology as only the empty set and the whole set. Okay, this is for the indiscrete. Now, for the discrete, we have that the topology is the power set of X. Okay, I also gave about the cofinite. I said the topology is collection of A subset of X uh, such that A is empty or A complement is finite. This is the cofinite topology. Now, I forgot to mention the usual topology, which of course I'm going to do in this video. Now, the usual topology is simply the topology formed with open intervals. Open interval of the form A comma B. Okay, so the usual topology is not actually the topology of all open interval. It's not necessarily the topology of all open interval. It's actually the topology formed with what open what intervals. So let's see an example. Let me form an example of a usual topology. Remember, in the usual topology, when we are talking about the usual topology, my X in question now, my X in this case is what? The real numbers. So the usual topology is also called standard topology. So some authors call it Euclidean topology. So it's either you call it standard topology, usual topology, or the Euclidean topology. So okay, now here I just want to form an example on the usual topology. So I have my empty, I have my whole set to be R. Remember, in my usual topology, the whole set is what? The set of real numbers. Now let me form an example. Let's say I have an interval 2, 3. Let's say I have an interval 2, 3, right? Let's just draw a line. So if this is 2, if this is 3, now let me increase this to 4. Okay, so if this is an open interval 2, 3, and this is an open interval 2, 4, now the intersection of 2, 3 intersect 2, 4, what will it give us? If we do this intersection, what do we have? We have that intersection will be what? 2, 3, right? Okay, now if I do their union, 2, 3 union 2, 4, what do I have? I have 2, 4, right? So therefore, this forms what? A topology. So this is an example of one of the usual topology on R. You can form as many topology. You can form the usual topology. You can form as many usual topology you want. Okay. So this is just a simple example of what a usual topology. Okay. So this satisfies the condition of it being a topology. Remember, for anything to be a topology, the empty set must be in the topology. The whole set must be in the topology. The finite intersection I equal to 1 to n must be in the what? Topology. And the arbitrary union of whatever that is here must be in the what? Topology. Okay, sorry the way I did it this way, but it's just a recall. So that's all for the usual topology. Now let's move into the main business. The main business is actually limit points. Okay, some people call it accumulation points. Okay, limit points or accumulation points. So let's call it limit point or accumulation points. Okay, now let's make a definition. Let X be a topological space. Let X be a topological space. Let X be a topological space and A is subset of what? Of X. Then a point a point x in x. Remember, where is the point coming from? The point is coming from the whole set. So observe this. Is called the limit point of the set A, which is a subset of x, if every open set. This if could be if and only if, okay? So this if could be if and only if, but just let's go with if. So if every open set G, if every open set, let's call that open set G, containing x, okay, containing x, then G must contain other points of A different from x. So we are saying that x be a topological space and A a subset of x, then a point x in x, so a point coming from x, is called the limit point of A if every open set G, every open set containing x, let's call that open set containing x, let's call it G, such that G must contain other points of A. So G must contain other points of the set A different from what? X. So other points that are not what? The element x. So let's solve this with an example so you understand better. Okay, now let's do it like this. An example. Let's say we have the set this is an example. Let's say we have the set x to be A, B, C, D, and E. Okay, and let's say the topology form here is the topology in question is the empty x singleton A, we have C, D, we have A, C, and D, and we have B, okay, we have B, C, D, and E. Okay, so this is the topology. This x is the whole set. This is the topology on x. Now we have A. Let's call our A to be the set A, B, C. Now observe that this is a subset of this. Now A is a subset of what? X. Now remember our definition. Our definition says that let x be a topological space and A be a subset of x, then a point in x is called that limit point of A. That is, if you pick a point in x, that point is a limit point of A if every open set containing that point, then that open set must contain other points of A different from what? X. Other way, you can actually define this as, or x in x and A subset of x implies that, okay, no, sorry. Other way you can define it that if let x be in x and A subset of x, then if x is in G, for every G open, if x is in G, this is another way of defining it. Let x in the whole set and A subset of x, then if x is in G, for every G open, then G difference the singleton x, G difference the singleton x intercept A is not empty. Okay, so the alternative way of defining this definition is let x be in x, A subset of x, then if x is in G, for every G open, that is G is an open set, then this is true. So G difference the singleton x intercept A should not be what? Empty. So let's solve this, but I will use this first definition to show this. Okay, now for us to do this, remember we want to find the limit points of the set A. Now there's something I forgot to mention. There's something called the derived set. The derived set, which is denoted as A prime, is simply the collection of all limit points of A. So it is the set of all limit points of what? A. So if I am able to find all the limit points of A, the set of all those limit points is called the what? Derived set. See, it is denoted as A what? A prime. Okay? So in topology, whenever you have something to be A prime or B prime or C prime, it is known as the what? Derived set in topology. So now let's solve this. Okay. Now watch this. Now we'll start from, let's consider A. Considering A. Remember, I'm picking my point from the whole set. So if I pick an element A, if I pick a point A from X, now if I'm considering A, now what are the open sets containing A? Look at the topology. Remember, the topology is actually the sets containing what? Open sets. So all these sets in the topology are what? Open sets. These are an open set, these are an open, all of them are what? Open sets. So what is the open set containing the set, containing the element A? We have the whole set, we have singleton A. What again? We have the sets A, C, and D. We have the sets B. Okay, no. This tree is okay. So the sets containing A are the whole sets, singleton A, and we have this. Okay, now remember the definition says if every open set containing what? X. Now these are the open sets containing what? A. Now let's see if this open set contain, let's see if these open sets, this and this, if this open set, if they contain other points of this A. Let's see if this open set contain other points of this A that is not the element A. Okay, now the whole set, this is X. X is defined as, X is this, right? Now does X contain other points that is not actually this small A? Yes. X contain B. At least X contain B and C. B, C. Even if it's just one, it's okay. So X contain a point B and, okay, let's say B that is different from what? A. Okay, now let's look at this singleton. Now observe that, does this singleton set contain other points of the set A different from the element, that small A? No, this singleton does not contain any other points. Okay, it does not contain B or C that is not what? A. It contains A actually, but we are looking for other points different from what? A. So therefore this small A is not a what? A limit point. Although if you look at this now, look at this open set here, look at this open set, you see that this one contains C. Actually this contains other points of A that is different from what? The small A. So it contains what? C. Okay, it contains C. But the problem here is that A is not a limit point, because remember we say for every open set containing what? A, those open sets must contain other points of A different from what? Other points of this set A different from the element we are considering. Okay, so since it fails at this, then this small A is not a what? A limit point. So the next one we are going to do is we are going to consider, okay, so we can conclude, we can say let's conclude this. Sorry, we say A in X is not a limit point since there exists a singleton, okay, that does not contain, since there exists a singleton that does not contain other points of A different from the small a we are considering. Okay, so this is the conclusion I will give for that one. So now let's consider B. Considering B. Okay, we are considering the next one. We are considering what? B. Now if we consider B, what happens? If we consider B, now what are the open sets containing B? The open sets containing B in question will be the whole sets. The open set containing B will be the whole sets. Which open set containing B? This will also contain B, right? So we have B, C, D, E. These are open sets containing what? B. Now let's check if these open sets contain other points of A different from B. Okay, so does this open set contain other points of this A different from B? Yes. X here, X is simply A, B, C. Remember, X is A, B, C, D, E, right? Now X contain other points of A different from what? B. X contain A, X contains C that are different from what? B. So X is qualified. Let's see if this is qualified. Now these two contain C. This set contains C here. So I can find C here that is different from what? B. Okay, so since I can find C here that is different from what? B, then this set is also what? Qualified. So we can now conclude that since for every set here B is what? A limit point. So B is a limit point since every set containing B contains other points of A different from B, different from the element B. Okay, so B is a limit point. Now remember, let's pick another point in X. Now if we pick another point in X again, we'll pick what? C. Okay, let's pick another point in X. We'll pick what? C. So we'll do considering C. So the next one is considering C. Remember, we are picking points in X. We're picking points in X. We're just picking points in. We've picked the first one. We picked the second one. So we want to pick the third one. Considering C. Now, what are the open sets containing C? We have X. We have set CD. We have ACD. We have the sets B, C, D, and E. Okay, so we have this. These are open sets containing what? C. Now the question is, does all these open sets contain other points of this A that is different from C? Does all these open sets contain other points of this A that is different from C, that is not C? Now X contain other points of C. X contain A, X contain B. That is not actually C. This one does not contain other points of A. Is there any other point of A that is here that is not actually this C? No. This does not contain, D is not here now, so definitely C is here, but remember what we are considering is C. We are looking for points that are here that is not actually what we are considering. So what we are considering in question is C. So we are looking for points that are in A that are here that are not actually what we are considering. So since this does not contain other points, it is enough to say that C is not a limit point. Once we find where it falls to be a limit point, we can now conclude. So there is no point checking here again, because from here alone we have seen that it fails at this point. So we can now conclude, to save time, you can conclude that okay, C is not a limit point since they exist this set such that this set does not contain other points of A different from what? C. That's the conclusion. Okay, so the next one we're going to do, considering what? Considering A, B, C, D, E, right? A, B, C, D. Yeah. Remember, the next one we're going to consider is D. Okay, we'll consider what? D. Now, what are the open sets containing D? Open sets containing D are the whole sets C, D. What again? Open sets containing these are the whole sets C, D, A, C, D. What again? B, C, D, and E. These are the open sets containing what? D. Please let me conclude. Is not a limit point. You can just write the remaining ones I just said earlier, the way I said you should write it. Okay, I said that to conclude that C is not a limit point, you say they exist this set such that this set does not contain other points of this set A different from what we are considering C. Okay, now considering D. Now, what are the open sets containing the element D? The open set containing the element D is this, right? Now, what we want to do now is to see if all these open sets, if all of them, if this contain other points of this set A that is not D. Now, this of course contain other points of this set A that is not D. It contains A, it contains B, and it is inside here. That is not what? D. It contains even C, that is here, which is not D. This one in question 2 contains what? C, here, that is not D. This one in question contains what? AC, that is not what? D. This one in question contains B and also C, that is not D. So it means that every open set here contains other points of A that is not what? D. So D is a what? A limit point. So you can now give your conclusion that for every open set here, for every open set here, this open set contains other points of this A that is not what? D. So D is what? D is a limit point. Okay, and lastly, we are going to consider the last limit point, E. Okay, we'll consider the last limit point, E. So considering E. Okay, now we are going to look for open sets containing E. So the open set containing E is going to be X. The next one is going to be, what are the open sets containing E here in the topology? So we have the whole set X. We have B, C, D, E, the set B, C, D, E. Okay, now we want to check. Remember, let me write them out. The limit point in the first one is B, second one is D. So okay, we have our B and D to be the limit points because I want to form my derived sets. Now these are the open sets containing this is the open set containing containing E. Now, does this open set contain other points of this set A that is not E? Yes, X contain other points of this set A. X contain A, B, C. They are here. That is not what? E. This one too contains B and C that are not what? E. Even if this one alone contains only B, it is still enough to show that this one contains other points of A that is not what? E. Okay, so this to satisfy the condition that it contains other points of A that is not actually E. So therefore, E is a what? A limit point. And because of that, we can now conclude that E is a limit point because for every open set, that is for every open set X and this set contains other points of A that is not what? E. So E is a what? Limit point. E is a limit point of what? Of E. Remember, all those conclusions I make, they are limit points of what? Of E. So B, D, E are limit points of E. So our derived set, remember our derived set is what? Our derived set is defined as the set of all the limit points. So our derived set will be B, D, and what? E. Okay, so our derived set is the set of all the limit points. Now let's move over to another example, a nice example. Let's say let's consider the usual topology. Let's consider the usual topology. Let's say let my X, remember we are considering the usual topology, so we are looking at the rail. Okay, and let X equal to R, and let's this be the usual topology, and let my A be a subset of X where my A is the what? The rational, the set of rational numbers. Now the question is, what is A prime? You know, of course, when we say A prime, we simply mean what is Q prime, right? Okay, that's the question. What is A prime? So what is the derived set of A? That's the question now. Now, remember, we are talking of rational numbers. Rational numbers is defined as the set P over Q such that PQ is coming from the integers and Q is not equal to what? 0. So it's the set of P over Q such that PQ is coming from integers and Q is not equal to what? 0. Actually, we may not use that definition, but still, let's understand what a rational number is. Now, we want to find the derived set of A. Now, the first thing we are going to do, remember, to find the derived set or to find the limit point of A, the first thing we are going to do, we are going to remember from the definition of the limit point, it says that from the definition of limit point, let's go back to our definition again so that we will understand what we are doing. So that let X be a topological space, and then remember, let S be a topological space and A must be a subset of X. Then if we pick a point from the whole set, whenever you are doing limit point, you must pick a point. The point in question we are looking for, the point in question must come from the what? The whole set. Then X in X is called the limit point of A if every open set G containing that X, G must contain other points of A different from what? X. Okay, so now let's work on this. Okay, let's work on this. So we want to find the derived set of this. Now this is what we are going to do. We are going to say let X come from what? R. Let X be in R, and let G be A comma B, be any open interval, open interval in R. Of course, an open interval is an open set. Okay, an open interval is what? An open set. That is why I said let G equal to A comma B be any open interval in what? In R, such that X is in what? Is in G. So I'm making a construction where x is coming from the real, and let G be an open interval. Remember, an open interval are open sets such that x is in what? Is in G. Now, remember, in our usual topology, the open sets are what? Open intervals in our usual topology. Remember, the first at the beginning of the class, I made mention of usual topology. I gave an example. So now this is an arbitrary interval. This is an interval. We don't know what the interval looks like. Now, one thing for sure we know is that by the properties of a real number, every interval contains an infinite number of what? Rational numbers. So if I pick an interval a comma b, then I can find, then there are infinite number of rational numbers in this interval. So let's, if I have 2 comma 3, then there are infinite number of what? Rational numbers in this what? Interval. If I have 4 comma 5, there is an infinite number of rational numbers in this interval. Okay, now this is just an illustration to tell you that there are infinite number of rational numbers in this interval. So by the properties of a real number, okay, there are infinite number. By the properties of a real number, there are infinite number of what? Rational numbers in this interval. So but by properties of R, we have that a comma b contains an infinite number of rational numbers. Okay, so a comma b contains an infinite number of rational numbers. Remember we said let x, remember we said let x, okay, such that x is in G. Remember, x is in this interval. So it means that for any open interval, remember this a comma b is G. Remember, this my a comma b is actually what? G. And this G is representing any open interval. So it means that for any open interval I pick containing x, it means that for any open interval a comma b, which is G, and this G contains what? X, it means that I can find at least one rational number, okay, that is not equal to x, but is in what? The set of what? Rational numbers, Q. Okay, it means that I can find at least one rational number in this open interval that is not equal to x, but is in the what? Set of what? Rational number, Q. Let's say we are considering 2 comma 3. Okay, supposing my x is 2.1, my x is in question is 2.1, then my rational number, then I can find let's say 2.5 that is in this interval, okay, that is also here in the set of rational number. Okay, so it means that if for every open interval a comma b containing x, and remember the open interval contains an infinite number of rational numbers, it means I can find a rational number that is not equal to x, because it's containing an infinite. X is just one value here, okay, x is just one value here, so I can find an infinite number of what? Of a rational number. I can find at least one of them that is not equal to x, but is in the what? In the set of rational numbers. So this now implies that x is a what? Limit point. Remember, a comma b is representing any open interval. So this means that there exists, let me say this means there exists, means that there exists a rational number p naught in G such that p naught is not equal to x and p naught is in what? Is in Q. Okay, so this means that there exists a rational number p naught in G such that p naught is not equal to x and p naught is in what? Q. Hence x is a limit point of what? Q. Now, but x is a limit point. We are not done. Since x is arbitrary, or we can say since x is coming from R, then A prime is simply the whole set R. Remember, x is coming from what? R. And if you exhaust all the points in R, all the points in R is a what? A limit point of what? Of Q, or simply A. You can call it Q or A. Okay, and all the points in R is a limit point of Q. So it means that if all the points in R is a limit point of Q, therefore R is the derived set of what? Of the R is simply the what? The derived set. So our derived set is what? R. So therefore, which is equal to our Q prime. Okay, so the derived set in question is what? The whole set R. Thank you very much for watching this video. I will really appreciate if you like and subscribe and also share to your friends. Thank you.